Do I need to restart? Do you have enough?
Ja.
Okay, should we begin? Yes, so everyone, welcome to ITRL and the Breakfast Seminars. Today we have Frank. He will be presenting us the findings that he has had on the automated vehicle traffic control tower. So we will basically join him in discussing what happens when you try to balance automation and human expertise or does it lead to a safer transport system. The agenda today is that Frank will present till 9:10 and then we will open it for discussion. We will talk about it a little bit till 9:25 and further from there we will have an open mingle session, so stick around and talk with us and maybe talk a little bit more with Frank. So yeah, here we go.
Alright, thank you, Bhavna. Thank you all for coming out early this morning to hear me talk. So, as Bhavna mentioned, my name is Frank. I have been working as a research engineer here at KTH with the Division of Decision and Control Systems and ITRL. I will soon start my PhD with the Division of Decision and Control Systems. So you'll probably hear more from me here. When I first arrived to KTH early in 2018, I met with Jonas Mortensen here in the audience and my other supervisor, Carl-Henrik Johansson, and they proposed to me a couple of different projects that I could possibly work on, and one of them was the automated vehicle traffic control tower. And then, as you know, I decided to work on this project, but to be honest, when I decided to work on it, I had no idea what the traffic control tower was, what it was supposed to be, and my gut feeling is that many people at that time also did not really know exactly what the traffic control tower was supposed to be. And so a lot of our work in the last year or two has been on developing the what, when, how, and whys of the traffic control tower, and how we should shape the control tower concept and introduce it into the transportation networks as they are now. So starting with the what. That's very loud. I have no control. Okay, bear with the sounds. So in our minds, one of the primary functions of a traffic control tower is to act as one of the exception handling layers for automated vehicles. And for example, we have this automated vehicle here on KTH campus that has encountered this strange yellow bus that is always parked there. And I will be a little bit more precise later about why this vehicle might have encountered this situation as an infeasible situation. But if it does encounter it as an infeasible situation, then since these are situations that we aren't preparing for a priori on the engineering side, we need to have flexible ways of handling the scenarios and resolving the scenarios. And so here I have just depicted me taking this vehicle and overtaking the accident and using my human awareness and my flexibility to resolve the scenario and return the vehicle to a position where it can continue its automated functionality and not have to be managed by a human operator. Disclaimer, this is not a real automated vehicle. That would be very nice. So, and I will spend the rest of my time today unpacking kind of this flavor of the control tower. And that is how the control tower should handle responding to infeasibilities that automated vehicles possibly can handle. And the reason why I specify this is that we believe that the control tower has many potential outlets and a lot of different applications. And there's a lot of reasons why you should include it, but we'll be focusing specifically on these infeasibility handling. So if we try to shape our concept of the automated vehicle traffic control tower, there's a couple of sources of inspiration that we can look to in other industries. So for instance, in Scania, this is a figure from Scania where they depict a control tower where they use this tower to manage their services and their operations. And many robotics companies are setting up very similar structures of setting up these control centers so that engineers or trained operators can wait for robots to encounter some kind of problems or even proactively manage the robots. And then one model that we all are familiar with that has been around for a couple of decades is the air traffic control towers. These air traffic control towers have been proven to be very critical in the safe and efficient operation of semi-autonomous airplanes. Airplanes can do, nowadays, they can do many of the functionalities that they need to do automated, but we still plan to keep humans in the loop centrally via these control towers. And this is a very important philosophy that I think that we can transition and transfer to the control tower. And then a more simpler model, maybe not more simple, but a call center. So call centers are set up for many companies and many products so that whenever products or product use creates infeasibility for customers, there are ways for the customers to reach out to human operators and ask them how to fix their problems. And this is important because for two reasons. The human operators create very organic interactions where the humans feel very comfortable. And then also these operators, they encounter many of these problems that the software or product has and are able to flexibly handle this in a way that the software can't handle itself. So if the software encounters its own system failure, it's very hard for it to detect this and to handle it itself. So that's why we have these external ways of helping. And so if we go back to the air traffic control tower, I found this quote from a book that was written about when 2 decades ago, or 3 decades ago. 2 decades ago. Took me a second. Where they discuss why we have the air traffic control system in the way it is set up now. And I think it's very nice. And they say that essentially that they believe that it's impossible to bring up the reliability of a system up to infinity, or even to accurately estimate that level when it is quite high. And this has a profound implication on the introduction of automation. That is, one must introduce automation under the assumption that somewhere, sometime, the system may fail. System design must therefore accommodate the human response to system failure. And this is a very important philosophy that they've maintained, that though we build these systems as best as we can and we continue to develop them, it's not reasonable to try to stack the automation capabilities more and more and assume that this is eventually going to be okay. We need to have some kind of outlet and some kind of flow for the exceptions to flow to humans, because humans in the end are the best critics of human built systems. And these system failures are something that is also often discussed in the machine learning community now, where I have kind of drawn this very abstract graph where I am graphing out on the y-axis the frequency that certain cases might happen that an automation system will encounter, and have ordered it from greatest to least. And for automated driving, for instance, on the left hand, we include things like the automated vehicle encounters stop signs or traffic lights very often. And this is something that we have a lot of data on. This is something we have a good grasp and understanding of. And if you go towards the right, then you get cases like in 2017 when Volvo was reporting that it was working on handling kangaroos in Australia, because it turns out that the automated system the automated systems on their vehicles were having trouble handling kangaroos and the dynamics of kangaroos. And this is important because we aren't clear whether this edge case tail is something that we can actually collect enough data to completely diminish down to zero. And this becomes most important when you consider cases like the kangaroos, where if you encounter these problems somewhere in Australia, even though this may not be a very big occurrence globally, relatively to the occurrences that happen globally, then it still has a huge impact, because it impacts how we trust the systems, and it also impacts how we need to handle the exceptional handling of the systems. But if we go more specifically to the control tower and about where we think the infeasibilities will come for the control tower, that the control tower could support, we have listed out 4 different classes of these control towers, and I will go through thought experiments for each one and detail each one a little bit more. So starting with these arbitrary legal constraints. These come hand in hand with the fact that laws in civil engineering cycles are not tied hand in hand to automated vehicle cycles, development cycles. So as automated vehicles change, as their capabilities change, our road networks and our city laws, transportation laws, don't update quite as fast. There's a lag time. And what I have depicted here on this side is maybe a case that could happen here in Sweden, where a vehicle, an automated vehicle that I have labeled Svea, because these are the automated vehicles that we have developed here in our lab, encounters an accident, and this accident is blocking its lane in a bidirectional 2-lane road. So this means that the vehicle cannot proceed on its own lane, and it has 2 options. It can either use the oncoming traffic's lane, or it can go off-road. It's clear to us that you shouldn't let an automated vehicle go off-road, because this is outside of its operational design domain. And for going into the oncoming traffic lane to overtake this accident, it's very plausible to think that a city would set up a law to disallow vehicles to go into the lane of oncoming traffic, because this is a very nice way of maintaining safety and variances. If you guarantee that the vehicle never goes into the other lane, then you can know that this vehicle won't be creating fatal accidents in these type of scenarios. And so in this case, due to the restrictions on the vehicle, it's reached an infeasibility that it can't resolve on its own. And this is where the control tower would have to come in, because the laws that apply to automated vehicles will likely not be the same that apply to humans. And this mainly boils down to the fact that we probably should not let automated vehicles decide when they should or should not break laws on their own. And this is something that should be tied to human decision making. The next class of examples that we have is heterogeneous traffic. So something that has come up on the news repeatedly in the last couple of years as automated vehicles have been tested on public roads is this phenomenon that as awareness has increased about automated vehicles, people have also started to act more irrationally around them or started to bully them, so to speak. So here, this is a quote from Uber's operation in Phoenix, where they found that when people identified the automated vehicle as being automated, then they would start to interact with it very abnormally, outside of their normal behavior. And we see this here in Stockholm too with Nobina buses, where as soon as people know and are aware that these Nobina buses are built to be safe, then they start doing things like jumping out in front of it and just stopping its operation, which is something that we can't allow if we want these systems to be efficient. And so the example I've illustrated here is an example where an automated vehicle is trying to overtake a human-driven vehicle. And the person realizes an automated vehicle and then rejects the overtaking action, and is actually, in this case, it's quite dangerous because the human-driven vehicle has control over the automated vehicle technically, because the automated vehicle is designed to be very rational and very safe. So if the human-driven vehicle, for instance, slows down or goes faster, the automated vehicle will always comply, whereas a human may not actually always comply, and we understand this from our day-to-day interactions. And in this case, the control tower has a role as well, because then it can connect to the automated vehicle, interact with the human-driven vehicle more organically, or even take an alternative approach of just contacting the human-driven vehicle. If some person is talking to you all of a sudden and asking you to stop interacting with the automated vehicle in this fashion, then it creates a very strong accountability or accountability for this human. That's very different than when you just have an automated vehicle. Yes, and of course, homogeneous traffic conditions would solve this problem, but this is not something that research has shown that this is not something that we should wait for, and we can't just do a binary switch between homogeneous or heterogeneous and homogeneous traffic. And then we get into the social and cultural complexity of our road networks and phenomena that happen on our road networks. Here I've shown maybe some construction workers have left out cones to close off this lane. And for us, if you were driving, it may be a little ambiguous at first, but I think most people would understand that this lane is being closed off and you're supposed to use the oncoming traffic lane as your lane that you should be driving. But it's very hard to characterize this for an automated system, because it's hard to understand a priori how a human leaves out cones for closing off lanes. Of course, you can set up protocols and standards, but since, like I said before, our roads can't be perfectly prepared for the automated vehicles, this is not something that we can just expect from an engineering side. And then at the same time, it's not clear and it's not proven that we can actually develop automated systems to comprehend scenarios on the level that humans can. This is something that is very open still. And then we have these situations where we actually should not let automated vehicles operate on their own yet. And this picture I have shown here is just a scenario with a parking lot where there's pedestrians going in and out of the parking lot, human-driven vehicles driving to park wherever they would like. And in this case, if the automated vehicle is actually designed to be safety critical, since we have very poor models about how humans behave and predicting where humans will be, in many of these cases, actually, you end up with an automated vehicle that just stops. It doesn't operate because it doesn't know that this human won't just start walking backwards, or it doesn't know that this human-driven vehicle will act actually fairly rationally. And in this case, a human operator would be able to actually go in and, again, negotiate with the humans. It would be able to nudge the humans in some safe manner, or it would actually know to expect that a human reading a newspaper won't just start running forwards as fast as they can. So these are these are some classes that we have identified for automated vehicles, and as we have developed these classes of infeasibilities, one thing that became very clear is that our problem is very different than air traffic control. So unfortunately, we can't just copy and paste all of the methods and protocols that they developed to our system. Some of the reasons why it has to have are closely tied to the classes of infeasibilities I just brought up, and that is, for instance, for ground traffic, we actually have so-called adversaries. In air traffic, you could, but it's very rare that actually there's some entity that is acting and making decisions outside of your control. But on the ground, we have very little control over animals, over pedestrians, over other human-driven vehicles. And also because of how our environment will be very highly dynamic, and a lot of the infeasibilities we need to solve require a lot of information about our very chaotic environment, then we also need to have these operators have a very low latency connection to the remote, to the automated vehicles, because it's also a better economic case to argue that these operators should be remote because you can scale up. And then if you have remote operation, then you also need to start considering much more advanced user interfaces than the ones that are used, for instance, for air traffic control. And situational awareness is something that you have to, it's just much more sensitive in this case. And so we then take an example from our, because I'm talking a lot about why we should have an automated vehicle traffic control tower, but to understand how and when the traffic control tower should be intervening on the operation of automated vehicles, we take the accident example from our classes that I just presented. But we look at a variation to make it kind of slightly more interesting, because the case that I mentioned before, it's very clear that the automated vehicles should just ask directly for help immediately from the traffic control tower. And so to have a little bit more information and clarity about when automated vehicles in more complex situations would need help, we create a variation where we actually allow the automated vehicle to overtake the accident, as could be the case. But of course, in our formulation, we will request that the automated vehicle only overtakes the accident when it is absolutely sure that it is safe to do so. And so we give we have a Dubin's car model for our underlying dynamics to keep things very simple. And then we consider also visibility, because this is something that we have to consider if we want to be realistic about how these automated vehicles will be operating. So when we put the accident back in, then we start to notice a couple of things that are very important for our case. So when the accident is placed back in, there's actually a significant part of the road that is occluded from the vehicle's perspective. And the reason why this is very important for a safety critical analysis of this scenario is that technically, because of this occlusion, the automated vehicle does not know that there is not a vehicle in its region of occlusion. And so if it is to overtake this vehicle, then it's very possible to run into this situation, because you've made a decision that could be one shot because you may not be allowed to just reverse arbitrarily because someone is either tailing you or just because it's not good to reverse on these road systems. So you could end up with a situation where you overtook the vehicle and then there is an oncoming vehicle that is breaching your safety invariances. We could solve this with adding infrastructure. So with sensors and roadside sensors or connectivity sensors, then the vehicle would have full information about the overtaking scenario and it could actually overtake it and would not need the control tower's help. But of course, if we consider more realistic or limited placement of sensors, you could end up with these situations where there is a sensor that will assist the vehicle's perspective and expand its knowledge base, but will still leave occlusion zones on the road network. And we can still place some dangerous phantom vehicles or potentially dangerous vehicles in these occlusion zones. And so the reason why we have set it up like this is that we want to understand with the kind of how the roads could be set up when the automated vehicle would actually be able to complete the task on its own and when it would actually need to ask for help from the traffic control tower. And to do this, to set up this mechanism, we connect to this mathematical tool called Hamilton-Jacobi reachability that is used very often in air traffic management, where in the early 2000s it was used to set up systems for collision avoidance on airplanes where you could actually have guarantees that in 10 to the 9 years that you would only have one collision. So these tools are very powerful in the sense that they're addressing safety problems at its very core in its formulation. I won't go into too much detail. There is a very nice paper written as an overview on this mathematical tool, but I will just introduce some terminology that I use for the rest of the slides. So we first define a forwards reachable set, where this is the set that we are using, that we're computing, that basically starting from the vehicle, the forwards reachable set are all the states or all the positions of the vehicle that the vehicle can reach in time t, given its obstacles, given its constraints. Then the backwards reachable set is the set of states. It's kind of the symmetric case of the forward reachable set. It's the set of states that can be from which a goal can be reached. And it'll be a little bit more clear of like why I'm using these reachable sets. But essentially, the forward reachable set will allow us to analyze when it's actually possible for our vehicle to overtake the obstacle or the accident without risking this dangerous situation with the oncoming vehicle. And the backwards reachable set will actually will complete this feasibility check because it'll give us a control policy that actually corresponds to feasibility check. Because of course, if you do this feasibility check and then you have a very inefficient way of controlling the vehicle, you could just end up in an accident anyways. Then to inspect this case, we first look at the classic way of looking at it, where we assume we actually have full information. We assume we can see everything. We assume we can do the full control problem that we want to do without any limitations. And then we can compute these reachable sets. Later in the discussion, if you guys are interested about the details of these graphs, we can discuss it further. But basically, the green blob here are these reachable sets. So starting from the goal position, the starting position is here, and the goal position is on the other side of the block. And what we're computing is we're propagating and simulating where the vehicle could be if it starts from the goal position and goes backwards in time, and starts in the initial position and goes forwards in time, so that we understand when it's possible to complete this. And it'll be a little bit more clear why we use this tool in a bit. And then, so then, like I mentioned, we can use these backwards reducible sets to then compute a control policy for these vehicles. And then here, I start to introduce the implementation and the setup that we have here in lab. So for this work, we actually have built a traffic control tower that you guys can feel free to look at after the talk. And then we have also set up these small scaled down vehicles that we call the sphere cars that match the signals and the information that a full-size vehicle would have, but on a much smaller and relatively cheaper platform. And so here we have modeled out the interaction that I just mentioned, and the vehicle, of course, trivially can complete the task because it has the full information. So, but we don't have the full information. And so, because we have limitations on the vehicles or the ego vehicles perspective and on the infrastructure's perspective, we have to figure out how to organize our behavior. We have to figure out how to, if the ego vehicle cannot complete the task, then it needs to ask for help from the infrastructure. And if the infrastructure can't complete the task, then we need to contact the control tower. And so we need to set up this sort of behavior chain, where if it's infeasible for anyone, it propagates to the higher authority. And whenever the task is complete, or the exception handled, we go back to the ego vehicle so that they can return to their automation. So to go back to the first case where we are considering the ego's perspective, which is a very limited and occluded perspective. So here we've drawn again the occlusion region of the road. Then we can put a obstacle in our formulation that models the potential vehicle that we can't see. And we can give this vehicle the same dynamics because we are assuming the worst case that it's another vehicle. And then here we can see actually this red obstacle wiping out the green zone. And I can maybe play this again. Before it actually propagates over to the goal position. And so this is kind of our way of modeling and showing that in this case, given the occlusion, that it's not possible for the vehicle to complete its task. And of course, this is the symmetric case of going back from the goal position to initial position, and it won't make it either. So then we consider when the infrastructure has a good placement, then we can see that the green blob here is able to propagate over to the goal position before the occluded potential worst case scenario vehicles actually make it to the meeting point. And then we can see here that actually from the goal position that we can compute the backwards reach of the site, and it contains the initial position of the vehicle as well. And so then we also set up a similar experiment where here we are logging the vehicle's decision making and the behavior, logging an output log of the behavior that is implemented on a meeting vehicle, where it asks for help from the infrastructure, and then the infrastructure completed the task for it. So then we get into kind of the meat of the our case study and the scenario that we actually care about, and this is how the control tower, when the control tower actually is, the assistance is actually required. So here we have a setup where the infrastructure sensor is limited. We place again a vehicle in the occluded zone, and then we do the same computation, and we see that actually the green blob makes it further than in the ego vehicle's perspective case. and we can probably just skip through the backwards reachable set. And when we implement this, we see that first the vehicle asks for help from the infrastructure, then the infrastructure, it's also infeasible, and it asks for assistance from the human operator. And then the human operator can then take over the accident. And one thing that is still unclear and not fully formalized is why the human operator would be better at completing this task than the automated system. And we claim that the difference here is tied to what I introduced in the beginning, that the human operator is the appropriate, the trained human operator is the appropriate entity to decide when the laws can or cannot be broken, or when a situation is safe or not. And that the human operator should be the final authority on these types of situations instead of an automated algorithm. And so we claim that essentially that you can keep setting up more and more automation. You can add more automation to the infrastructure. You can add different multi-agent collaboration. I think that's from me.
Is it the car needing help?
Yeah, it's the car requesting assistance. You can keep adding more and more to this automation stack, but ultimately the structure that we need to set up is to cap off, so to speak, the behavior specification of the automation to end at the AVTCT always. And this is mainly because of the fact that the AVTCT technically or formally doesn't have, we assume that it can handle all situations. And so this is why all infeasibilities and exceptions should always finally end at the AVTCT, and we should always have this starting and ending positions in our behavior. And so our conclusions from this work is that the traffic control tower is a very critical part of the transportation network. And it's something that it's not really optional if we want to consider these safety critical scenarios, or if we want to consider the exception handling. It's not something that we can just leave out and then try to engineer a solution to keep patching up and fixing the exceptions that we've encountered in the past. And that the control tower should always be at the end of your finite state machines or your behavior. It should always be this final stop. Furthermore, we start to understand, as we have studied the control tower more and more, that there's this duality and this trade-off between the capabilities of an automated vehicle and what a human operator can do. And there is, of course, overlap, and we need to characterize more precisely in the near future what the overlap is and what the human operator is actually more capable than the automated vehicle at doing. And then we also need to understand how machine learning might actually transition and shift around this duality, because you can imagine that as human operators handle more and more cases, that we should learn this for the automated vehicle, that they should learn from the human operators more and more. And so my point being that these two sets of capabilities are very dynamic and change a lot. And even as AV capabilities increase, it's also very likely that human operators, their capabilities might even increase and change as well. We have seen this throughout history, that as technology advances, humans don't just stay static. We also respond and adapt, and we also change a lot. So I think characterizing this duality will be a very important near future work. And then at ITRL we have set up this this initial platform and this system where we have set up the different modules of the control tower. And we have also identified that there's a lot of work to do on different modules, and so we are working with a lot of partners at ITRL to fill in a lot of these modules and to connect more and more technologies to try to complete this picture more and more. And then for my actually for my PhD topic, I will be considering more complex setups. So in this setup, I have just considered a very linear behavior specification where I just have a single automated vehicle, a single infrastructure, control tower, and everything is previously defined very well. And we would like to actually understand in the real scenario, when we have many actors and many players, how these control authorities would actually be selected and how these behaviors would be dynamically structured. And also specifically more cases of understanding of how the vehicles ask for help in more cases than just this accident overtaking case that I presented. There have been, there in our current automated vehicle traffic control tower project, there are many different partners that I have to thank because they inspired a lot of this work and a lot of the development. And then, of course, special thank you to my supervisor, Carl Johansson, and then the project managers, Jonas and Rami, on this control tower work. But this concludes my talk, so thank you.
Great, so let's open up for questions. Frank. Yes, I will.
Okay, thank you very much, Frank. It was very, very interesting. And I get a bit curious about this, like, complementary functions of infrastructure, V2I communication, and AVTCT or control towers or human operators. And so if we have on a system level, if we want to ensure like minimize the downtime for automated vehicles, like I guess there are two things, like then the system, I guess there's a trade-off there between how much infrastructure should we have and also how much or how many operators should we have and what cases should we use them for. And have you thought anything about, like, because I guess that would change over time because building more infrastructure takes time. And maybe it's faster to scale up human operators. Mm-hmm. And then also from a cost perspective, what would be like, if Trafikverket would invest in this, should it bet money on building more V2I communications and sensors or more traffic control towers? And have you thought anything about that and how that problem can be approached?
No, you bring up a very interesting aspect of this that I haven't really considered before, is that yes, there's this temporal cost in all of this, that you have to trade off how much you spend on, how much time you spend on your infrastructure. We have actually mainly been focusing on trying to tackle just the scalability ratio between how many operators do you need for these applications and why how this ratio would behave. But unfortunately, I don't have any good answers for you, but it is something that we have been tackling a lot recently.
What is that ratio? So somewhere, in what range?
So I think from a safety critical perspective, if you have a safety critical application, this ratio clearly should be 1 to 1. Mm. What is not clear is because how safety critical something is it's continuous. It's not binary. Mm. And for instance, you could be taking approaches that like Einride is, where they, for safety critical parts or for the parts that are hard to automate, they have human operators always driving the vehicles, but the thing is that the vehicles are not always in those situations. So yeah, I don't really have a good answer for you. I think it's just something that's very, it's still something that's very open to us. Mm.
Yeah, not so much a question, but more of a thought or a consideration regarding like safety, like when will what you were talking about in the beginning, like when are like automated vehicles safe enough? And it's extremely hard for us to actually say that. And there have been, I read like one paper who estimated that you needed to run few vehicles like 100 years and 24/7 basically to like statistically prove that they're safer, since accidents actually don't happen that often. And I mean, it's pretty hard for us to actually deem when, okay, this task is now suitable to automate at all times.
Yeah, I definitely agree. I think so. This is something that is. So one thing that I didn't mention is actually that for air traffic control, they didn't really. They kind of took a very similar approach that is being taken for automated vehicles right now, and that they didn't. They kind of just kept testing, kept iterating their engineering and improving their systems, and during that time actually there was actually many accidents related to automated to airplanes compared to now. And so we had cases where airplanes were colliding in midair, colliding into other things, and one thing that changed this a lot was the development of a lot of new verification tools. So to your point, I really think it's very important that we take a very similar approach to automated vehicles, that we need to develop new verification tools because of what you mentioned. It's very difficult to do this.
I guess my question is also kind of, sort of related to that, but so in your system there's a lot of missing information that are collected. Some of the information that you collect is probably not correct, maybe from the sensors, and then you have some control mechanism that currently signals that now it's takeover. Or is there any value in handing over the information to the remote driver, and in what way do you communicate that information? Do you have any views on that?
So I think there is a lot of value. I think that it's much more difficult than communicating the information to another automated system, because you start to get into a lot about the psychology of an operator, how the operator, if I understand correctly, you mean like how the UI,
Yeah, all
like
these
what information?
Backwards, forwards, feasibility sets, and a lot of information. I mean, you have computed a lot of things, and you know something about the situation, but not everything, and you deem it unsafe, and but still there is information that can probably aid the remote driver. How do you communicate that? Is it worth to communicate, or is it just misleading maybe?
I think it's better to communicate it, but here we actually do very little communication of this information, and it's tied to the it's tied to the fact that it's very difficult to understand how to design it, because like you kind of noted, oftentimes it can be a lot worse. And I think that one thing that is still very open is we still don't know how to represent this information to a human operator. But I think it will be better, and it's something that should be done. Yeah.
Quick comment. I think this point that you mentioned, that it's still unclear why we are better to handle these situations than the vehicles. There might be some aspect to it that is connected to how do we handle, because I thought about it. If you're driving, I mean, how do you know when you're trying to take over that it's okay to keep going or not? There's a lot of motivation about like fight or flight, and how do we react to certain dangerous situations, while I think the SVIA cars would not feel like, I want to protect myself, right? I mean, the SVIA car or the automated vehicle. So I think maybe not until the vehicles have this kind of maybe sort of self-awareness, probably, that we can assume this kind of comparison. But because I thought first, I mean, you might think of like the vision, our vision that has took evolution maybe like hundreds of thousands of years, and our perceptions and those systems are newly born, but they are accelerating. So maybe in 10, 20, 30 years, they will be able to kind of harness this, but it will be interesting to know.
Yes,
So
I agree. Yeah, I think it will be very interesting because, very now getting a little philosophical. It'll be very interesting whether or not it's actually possible for us to comprehend ourselves
yes.
fully to be able to design science.
But is there a literature that says like, or like a line in literature that says that the vehicles will be able on their own to handle those situations in the future? Is it mentioned somewhere in the theories, or like in professionals, like I don't know, in the industry, as far as you?
Not as far as I know.
Okay.
Most of what I've seen is mainly hopes and dreams.
Yeah.
I'd say.
Just a comment on that. So the one problem is also that the operator is remote and distant from the situation. So the operator is not risking
Yes.
his or her
Exactly.
safety.
Yeah.
Exactly.
So it's more like running a game. I mean, there are results about that you're more willing to take risks, or you're not engaging enough in the safety if you're remote.
Maybe we need to make the room shaky.
Yeah.
So if you get an accident, you will
Electric shocks.
Electric.
And,
there are consequences for the remote operator.
Claudia, then Mia also had a question.
Yeah, my question was if you think that it's about really connected with what we are saying now, but do you think there might be a case where actually the human, even from the control tower, cannot decide whether it's safe or not, and then what should we do in that case? Did you think about that? Or?
Yeah, so I didn't mention this, but I think that I don't want to consider the human operator as a solution to all problems, but I think the key difference is that in the cases that the human operator also cannot solve it, they still have a course of action that they can take. They can report this to the authorities that there is some kind of it's hard to imagine. It's hard to on the fly to imagine a scenario where the human can't handle it. But if it is, then they can report this as if it's a big issue, then they can report it as an emergency. They can geofence the area off and prevent other vehicles from entering this area. So there's a nice course of actions that they can take. So I definitely think there are cases that the operator should not be able to solve as well.
Yeah, I just want to ask because when we say the AVTCT, so we are basically have this consumption is like these AVs is connected to the control tower, but there must be because we do not know, we are not there yet. So will be the scenario that there will be AV that are not connected to that. So I just want to ask, in your future scenarios, when it becomes more complicated, will you also consider that, like the unconnected AVs in this transport system, how will these two interact? Because for now, what you've given is, as you mentioned, is a kind of linear, and also is a traditional vehicle and the AV that is connected and can be controlled by the tower. So that could be something, at least for me, I think could be really interesting to think of.
Yes, I think so too. I think this would be a very nice thing to consider.
Another question about risk and safety. So, I mean, we take all the time risk when we're driving, and sometimes it becomes an accident. So, well, I don't know, there is some kind of a balance because we're trying to minimize the accidents, so maybe these systems should also take some risk and sometimes have accidents. How do you balance this? So for example, in medical imaging, computers are outperforming, statistically, doctors. Yet we still have doctors that are doing this type of work, and where is the balance? When do we trust the machine more? Or
Yeah.
have you thought about that? I mean, right now you just you trust your sensors, and
Yes.
you have a feasibility set, and you just take the maneuver. But maybe if you have like a little bit of gap, you can still take a risk from an automated system.
Yeah. No, I have thought about this, but I have no idea. Because it's hard to understand what approach to take this at. Like, should you look at it from an ethical point of view, or should you look at it from a cost optimization? So no, I have no idea.
Okay, last question from Albert.
There's a question to you, Frank, but maybe also for the other guys who've been involved in this control type project, and it's about accountability and regulatory aspects. So I guess from a legal standpoint, what you do is that you hand over the driver, you shift the driver from the automated system to the human driver, just as you would do in a level 3 automated vehicle. But have you thought about at what point will the operator actually become driver in the legal sense and also accountable for any accidents or bad things? Because I guess there's also some time for the driver to get immersed and comprehend the situation. And is it clear? Is the clear line when accountability should be switched? And how can we think about that?
Can you say the last point? Is there a clear line between?
At what point should you legally hand over the responsibility of the situation on the vehicle to the remote operator?
I think this is a project on its own.
Yeah, it's kind of wrong.
Because I mean, to me, it looks like to test these things, you need some closed arenas in order to see the consequence. Because what constitutes responsibility for traffic vehicle, for example? Then you need to check, and then you see in which line whose responsibility is at which point. Because I think when there was this accident before in Arizona, the question was like, whose responsibility is it? Was it the safety driver? Was it the brain? Because it seems like it's still unclear at which point whose responsibility is. It seems to be like flowing right now.
Yeah, but what or does something? My question is more like, because we have now regulation for pilot testing, and we have at least quite well developed practices and not practices, but ideas on how to do it with a human driver in the vehicle. But my question is more like, does that kind of take over process and also the handover of accountability change when we have the operator remote instead of in the vehicle? Are there different principles? Have you thought about this, or is it?
I think it's one of the workshop questions. Yeah, I mean, but it's still not fulfilled, I would say. But it's one of the important
But
questions.
the handover is very difficult.
Yes.
Yeah.
I mean, also to hand over to a human in the car operator, and sometimes this is deemed infeasible, and that you cannot do it. But you need to reach a safe stop, and from there you can take over. And maybe this is also what we need in this. I mean, to be able to immerse in a dynamic situation and take over might be impossible. Maybe you need to reach safe state before you can.
We can discuss more. That's good. Before you all leave, I would just like to tell you that we have more seminars coming up. The next one is a super interesting one from Einride on the 29th of October, and I would really encourage you guys to sign up. And now, please ask Frank more questions, get some more coffee, and just walk around a bit, and maybe if you want to see the demonstration, please go ahead and do that.
Thank you, Frank.
Good. Thank you so much.